Oh, I will. Sit down.
Come on, buddy.
You're not cool enough.
Wow, I get it, man. I'm
Alright, and we're live! Alright, so first we're going to talk about some triangles today.
Hell yeah, I love
Here we go. Alright,
Three-sided and one side's longer than the other.
Can you shut
not always. Alright, so here's the deal.
That'd be safe.
I can't see the top of that triangle.
Kendra, you want one?
Alright. Oh my god. Worksheet, father. Alright, here we go. We are live. We are starting. We've got triangle A, B, C,
Here you go, Wayne.
D, E, F. Why'd you give them so many of these?
Just to shut up your sausage meat.
Alright, so what does it mean for two triangles to be congruent?
The same. What?
I know.
Same
Sorry.
angles.
Can't stop, won't stop.
Same side, same angle.
Same size and same angles. So that means that we have matching congruent sides, right? And we have matching congruent angles.
Can I change it?
Cool? That's what it means to be congruent. Today we're not talking about congruency really, we're talking about something else. So, new stuff.
Does that mean about the same?
Here we go.
Okay, Justin.
So here's a triangle.
Get that off your screen. Wait, maybe? We haven't really out this week.
Right, check it out. No, we don't. So, we've got two triangles. Let's play a game. We're going to play a game of Don't Break My Stapler. Then we're going to play another game. Alright, game's over. And I'm the loser.
You're not, though.
What do you notice about these triangles? And we're going to see how many times you can tell me things that are true that you notice about these triangles, but is not what I'm trying to get you to say. So first hour did this for like 30 minutes straight of, I didn't want to know that, but yes, that's true. Third hour and fourth hour immediately said exactly what I wanted them to say.
They're both
We notice.
triangles. They're similar by ASA.
They're similar by ASA, that is not a thing.
They're both triangles.
They're both triangles, very good. What else do you notice?
They're similar.
It's an airplane.
You what?
You need to build an airplane.
Can you move there? Yes. I just can't hear. Nope, they're not. My sausage means two sides are the same. None of the sides are the same.
Bro.
They're also scalene.
They both have a right angle.
They do not, actually.
Can I make a better one?
They could. Actually, they do.
They have numbers and letters.
We haven't talked about that, Joe. Alright. What else do you notice?
They have numbers and letters.
They have numbers and letters, that's true. What else?
What do you want us to
I want to know what you notice about these triangles, and we're playing a game to see who can say the most things, right? Which class, but without actually telling me what I really want to know.
not get me sick, lady.
I'm not sick.
They're not touching each other.
They're not touching each other. What else do you see?
One bigger than Doritos.
What do you say?
One bigger than the other.
One's bigger than the other. What else? That's what she said.
Yeah.
One's smaller than the
One's
other.
smaller than the other. What else you got? They look like Doritos. Good job, Coach.
It goes from 1 to 10.
You're welcome.
Goes from 1 to 10. What does that mean?
The numbers on the outside. Those
No,
are
they
the
don't.
lengths. Those
They
are the
don't.
lengths.
Where's one? They go from.
Oh, it's half the size. It is half. No, it's not. Yes,
What
it
are
is.
you
No.
talking about, bro?
Yes, well, there's a 3 and a 6, a 10 and a 5, and a 4 and a 8. That's
Ding, ding,
half.
ding, ding, ding. The game is over. That is actually what I wanted to know about the triangles. Turns out that. Look. Okay. Look. I don't want to get.
I'm good for you.
Look. Okay. So we got two triangles, right? Is that the quickest it's been said? The two. Yeah. No. Second place. 3 and 6. The relationship is half or double, depending which way you're going, right? Double when we go from 3 to 6. Half when we go from 6 to 3. 4 and 8 match up the same way, right? Same thing with 5 and 10. They're either half or double, depending which way you go, right? Now, numbers are always related. All numbers are related. This is true. That's not amazing. How does 2 relate to 10? Well, it's times 5, right? How does 2 relate to 50? Well, it's times 25. How does 3 relate to 7? Well, 3 times 7/3 gets you 7, right? It's not amazing that numbers are related. All numbers are related some way. What is amazing is that all of these numbers are related in the same way. 3 times 2 gets us 6, 4 times 2 gets us 8, and 5 times 2 gets 10. Schlaffer, better be good.
No, I was going to ask, like,
Why do you have
the 3 and the 6 are in the same spot, but the other 2 are not.
There, but that's okay. You can imagine flipping this triangle and they'd end up lining up.
Why do you have a
Yeah, they do. But it
Kleenex
doesn't matter.
in your mouth?
All right, so
I got my confidence.
again, the idea is not that the numbers relate. This happens all the time, right? If I gave you a triangle like this and then 3 and 6 went together, great. So does 4 and 6, you'd add 2, right? So does 5 and 6, you'd add 1. They're all related. But what is cool, Schlaffer, thank you. We know that all these numbers relate the same way. When we talk about relationships, what we're talking about is ratios. We're talking about fractions. So, AB When I write a line over it, it means line segment AB, right? So we're talking about the segment, the figure itself. And segments have certain properties, right? They start and end here and here, right? Whatever. When I don't have a line over it, what I mean is I'm talking about the value of AB. So like when I write angle CAB, I'm talking about the angle. But when I write little m, measure of angle CAB, I'm talking about how much it measures, right? The degrees. When I don't write a line over AB, it's just telling me how much it measures. How much does AB measure?
5.
You're closer.
How do you know?
Now I'm comparing AB, and I can compare it to anything. But which one does AB match up with on this triangle?
FE.
FE.
Phi. Mm.
And FE is what?
And
10.
Feet.
So the relationship there is 5 versus 10, right? And we can write that as a fraction, which simplifies to what?
1, 2.
1 over 2.
How should you?
Now, I started on the small triangle and went to the big. I wrote AB over FE, small part over the bigger part. And so I got a half. If I had done it the other way around, big part to small part, I would have had 10 over 5, and 10 over 5 would have been 2, right? 2 over 1. Which question, Slaughter?
AB doesn't correspond to EF. You know what I'm saying?
Yes, it does. Why?
Kind of
How-
nice. We should have wrote a note.
They're not the same.
Angle A is equivalent to angle B.
Nope, not necessarily.
How do
Oh, my
you
other
prove that?
Doesn't have to be. Just because it looks that way doesn't mean it is. Okay?
So you just go based off of the numbers?
Yep. Go based off the information you have. So AB and FE are related. Let's go to BC. BC in the small triangle is 4, right?
B is equal
And then BC matches up with what on here?
to DE.
DE.
Is there a particular?
Technically, you can say that it matches up with any, right? 4 and 6 can go together, just the same as 4 and 10, but 4 and 8 goes together the same way that 5 and 10 do, right? So we have 4, and then DE is 8.
Is this like dilation?
No, but yes.
Does it matter?
Actually, yes. All right, so, yeah, good job. All right, so 4 over 8 is a half as well, right? We've talked about AB, we've talked about BC, last is to do AC. AC is the 3 segment, and it's going to relate to the 6 segment over here, right? Because again, the pattern is double or half depending on how you look at it. So that's going to relate to DF. DF is 6, and you'll notice that that is all in half. I'm not blowing anybody's mind here, I don't think, right? Again, I wrote small part to big part, so I got a half. If I had flipped all of these, I would have gotten 2 over 1, which is 2, right? Does that make sense? Again, it depends on how you look at it. Are we doubling it or are we halving it? Yes.
Does it matter when we do this? Can you, like, does that, if it's AB, does it have to be FE or can it be switched?
AB definitely goes with FE. You could flip these though, right?
Oh, like, could you say AB is equal to EF? Can you do that or no?
No, AB is not equal to EF. We know it's not.
Yeah.
It's 5 and 10. So, I haven't blown anybody's mind, but this can be written another way. So check this out. AB over EF. The way they relate is the same way that BC and DE relate. It's the same way that AC and DF relate. All right. They are proportional is what we say with that. So what does this mean? Well, you've seen this stuff before, but let me break it down. We have 2 fractions equaling each other. A single fraction is a rate or ratio, like miles per hour, AB per FE. That doesn't make any sense, but it's a fraction, right? A ratio, comparing one thing to another. When we compare 2 things, right? This to this and that to that, and we set them equal, that's called a proportion. So individually, that's a ratio, right? This whole thing is a ratio. All together with the equal sign is called a proportion, like porpoises.
Say corpses.
No, porpoises. A porpoise is a mammal that lives in the water. So examples would be dolphins, bosukas,
Don't.
narwhals,
Mammal.
blue whale, platypus. No.
I watched like 3
But that lives in the water, but not on.
Just kidding, this isn't about porpoises. It's about proportions. Proportions, what are they? They're 2 fractions compared to each other.
Yes.
So, when we have similar triangles, and that's what these are, they're not congruent, they're not the same, right? They're not exactly the same, they're definitely different. When we have similar triangles, they're related by their proportionality, meaning that they have sides that relate to each other all in the same way. 3 relates to 6 the same way that 4 relates to 8, 5 relates to 10. They all relate by a half, because AB over FE is a half, BC over DE is a half, AC over DF is a half. They all relate by the same way. So they're all proportional. They all relate by the same thing. When the sides are proportional, the triangles are similar. Kind of with dilations, right? Making something bigger, right? We dilate it by a certain amount. This is taking this guy and doubling it.
No, it was with the coordinates.
Yes.
Oh.
That was dilation. Of course. It's okay. So yeah, all of these relate. So what we're saying is that for triangles to be similar, their sides, all 3 of them, Don't have to be congruent, right? We're not talking SSS like SSS congruence, right? We've talked about that before. We're talking about SSS similarity. If all three sides are proportional, meaning that they all relate by the same way, right? Then we say those triangles are congruent. Triangle is congruent, or not congruent, but similar to another triangle. So congruency symbol is an equal sign with a tilde on top, right? Similarity is just a tilde. Okay? That means similar. Does it mean that they're the same? No, right? These are not the same triangles. They're different. One's bigger than the others, right? But they are similar because they're related by the same way. Each side matches up to another by a certain proportion, right? And the way we write that is this. AB matches up with FE. BC matches up with DE. And they all relate the same way. Again, if I write the small part on top, I need to make sure I write the small part on top for all of these. Yeah.
So like AC and DF are like the same side. But
They are, but they're not exactly the same.
yeah, okay, but CB and FE, they're like they're like switched. Like
Right, and that's
FE
okay.
goes with the other one. Is that gonna be how most of them
So
are?
I could flip it, right?
Yeah.
And then you wouldn't have an issue. So it's the same triangle, it's just turned on its side a little bit, that's all. That's fine. Again, all that matters is do the sides match up, okay? Good question. So another way to write this could be instead of doing the small parts on top, I can do the big parts on top. If I did that, I'd get this. FE relates to AB the same way that DE relates to BC, the same way that DF relates to AC. And what would their relationship be? If this is 1/2, this would be 2/1. Right? Again, the consistency is key. If I wrote AB equals DE, AB over FE equals DE over BC, I flipped one without the other, that wouldn't be true. Because this one would be equal to 2/1, and that would be equal to 1/2, right? If I flip this one. So you have to make sure that small stuff goes on top, right? Small triangle stuff goes on top, and the bigger triangle stuff goes on top. Or vice versa. Either way is true. Again, it depends on how you're looking at it. Am I doubling it, going from 3 to 6, or am I having it going from 6 to 3?
I wanna make a snowflake.
Okay?
Is this all the learning?
Kind of. So, side, side, side similarity. It means not all three sides are the same, because that means congruent, right? We know that's enough to prove congruency. Same dumb triangle, right? Side, side, side similarity means that the sides are proportional, and that's enough to say that triangles are similar. So let's talk about that. Pop quiz.
I don't like pop quizzes.
All right. Shapes class.
Yay!
What is this shape?
It's a
Circle.
It's a triangle. And what is this shape?
Square.
Triangle.
Octagon.
Because it has what?
3.
Angles. Very good. That's why we call it triangle, not tri-side, right? So we got 3 angles for each of these figures, so we call them triangles. All right, here we go. Here we go. Here we go. Here we go. Here we go.
Yeah, because if we go to the tri-side, it would actually be 6. There's 3 on the outside, 3 on the inside. Just think about that.
What do you know about the triangles? They're congruent because by side, side, side congruency, right? Regular SSS, these match up, right? We have 4 with 4, and
Good
we've
job,
got
Sydney.
3 with 3, and we've got 5 matching up with 5. So by side, 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 the triangles are congruent. Now my question for you is, they're congruent. Are they similar?
No.
No.
You say no! Why do you say no?
Can't be similar if they're the exact
So his argument is you can't be similar and congruent at the same time. Remember, in order to be similar, they need to relate in the same way. Does anybody dissent? Good, I will. Yes, they are similar. Why are they?
Because they equal 180.
Raise your hand so I can hear you.
Because
Laney.
They still have some like the same parts.
They're still proportional.
Yeah.
So let's mark stuff down. Let's call this A, B, so we can talk about it. B, C, D, E, F. All right, cool. So A, B relates to what on the other triangle?
A, B, D, E, D, F.
Yeah.
A, B relates to D, F. What's A, B
Wait, what
measured?
5.
5. What's DF measured?
5.
And when we simplify that, what do we get?
1.
1.
1.
Juan.
I know it's 1.
I've
BC relates to what on the other triangle?
Oh,
DE. What's BC and DE?
4.
They're both 4. What's 4 divided by 4?
1.
Are they all going to be the same?
What's AC related to the other
I think
triangle?
that is a yes.
3 over 3, right?
Yeah.
So is it true to say this? AB over DF is equals BC over DE.
Two cows, same move.
And AC over EF. Is it true to say all three of those are equal?
Yes.
Yeah, because they all equal the same thing. They all equal 1.
I guess I'll leave.
Is this what our test is about?
So they are, yes. So they are similar, right? Because
No,
they
they're
all
not.
have the same ratio. They're all proportional, just like this was. This was a proportionality of 1 to 2, right? And this is a proportionality of 1. So they are similar. You can be similar and congruent at the same time. When they're congruent, the similarity will be 1. Right?
That's automatic.
Automatic, right? If they're all the same, right? 5 divided by 5, 4 divided by 4, 3 divided by 3. I don't care if the sides are both 3.14 and 3.14. Any number divided by itself is 1.
You know pi.
Right? So if we have similarity of 1, that means that the triangles are congruent, right?
Is that
But
true?
they're still similar,
Is pi
right?
divided by pi 1?
Yeah, anything divided by itself is 1.
Really?
So
Really?
Pi?
So these triangles are similar. Are they congruent?
No.
No, they have different sides, right?
No.
These triangles are similar, right? Because they relate the same way, right? 5 to 5 relates the same way that 4 does to 4, relates the same way that 3 does to 3. Are they similar? Yes. Are they congruent?
Yes.
Yeah, they can be both, right? That's fine.
I'm so flaky.
Now again, I could have flipped these both, it still would have been 1 over 1, right? Doesn't matter. Both triangles are the same size. So yes, these are similar. So what we would say is by side, 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 and we can't write just side, 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 because that refers to congruency, right? And not always are things that are similar congruent, right? What we'd write is by side, 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 similarity. You can write SIM for short. You can put the dot there if you want. You can write out similarity like I did before. Or you can do a little squiggle by SSS squiggle. We would know that this triangle and this triangle are similar. Let's label them. Amy, what's your question?
So
How much side will
triangles, okay, they can be similar but not be congruent. But if they're congruent, then they are automatically.
Exactly. Yeah, they gotta be, right? Because the ratio would be 1 always. Right. Good point. All right, so let's compare these triangles. We got triangle ABC, right? And now we need to match up their parts just like we did for congruency. This is important because it turns out there's a CCP thing for similarity. It just won't be CCP because that's corresponding congruent parts, right? It'll be corresponding similar parts. CSP.
Oh, I don't like that. It doesn't sound good.
All right, so A is this right here. It's made up of the red side and the green side, so it's going to match with what letter on the other triangle?
That letter.
F. B is made up of the red side and the blue side. It's going to match with what over here? D. And then C is made up of green and blue, so what's it going to match up with? E. Cool. They're similar. These triangles are also similar, right? Because they have a ratio that connects them, right? They're all proportional. These guys are similar and congruent. So we can say by regular SSS, they're congruent.
Simple.
Cool. I'm glad you feel that way. Let's talk about what is enough to make things similar. So we know from congruency, that's the congruency symbol equal with a little tilde, right? We've got SSS, regular SSS, right? What other congruency postulates do we have?
CSCP.
Nope, that's not something we can do. That's something to prove the parts
SAS.
congruent. SAS, SAS, give me another one.
SAA.
SAA. We can also write that AAS, right? Forward and backwards is the same thing. What else do we got?
S-A.
HP.
SA is not enough.
HL.
A-S-A.
ASA.
And can you use the H1? HL?
And then we've got HL. The only one that doesn't appear is ass and ass backwards, right? Right? And HL is like a special case of ass, right? It's really made there. All right, so similarity is similar, right, to this, but it's not the same. All right, so what transfers over? We learned that SSS does. We call it SSS squiggle. That's my rapper name. SSS squiggle.
No.
So what else transfers over? Let's talk about it. Let's talk about it. So let's try SAS. So here's a triangle. Okay? It's got a certain side, an angle, and then a side, right? That's SAS, right? Let me make another triangle. Now again, we're not doing congruency here, we're doing similarity. So I don't want the same thing. I want something that I know to be similar. So I need two proportional sides. So the easiest way to do that, it's not very easy, but it is the easiest, is to make something like this. Alright, so check it out. I made these angles as small as I can make them without breaking the thing. Are the sides proportional? Yes, 2 versus 4 relates the same way that 1 does to 2, right? Double. Do we see that? They are proportional. Are they proportional now?
No.
No, because 2 relates to 4 a different way that 1 relates to 1, right? So they're proportional. The angles are the same, so I have matching angles and I have proportional sides. So I'm checking if SAS is enough to prove the triangles are similar. Obviously they're not congruent in this case, right? Now, will this be enough to say that the triangles are proportional? That they're similar? Yes or no? What do you think?
Well, right now the bottom one has 2, the other one has 1,
2 to 1, 4 to 2. Same ratio, right?
Oh.
Those are all good. Now, the only way we know to check is by triple side, right? I'm missing the third side here, but what do we know about these sides? They're kind of locked in, aren't they? Right? If I want to make a triangle with this, there's one way to do it. However it takes to get from there to there, right? Same thing here. So if these two sides are proportional, I'm locked into another side, it's going to be proportional as well. So SAS kind of gets you triple S, right? It locks in that last side. So if we have side angle side, we know that that's enough to prove it similar. So by side angle side similarity, these two guys have to be similar.
Would you use your CP or CSP?
You can do that to prove the other sides would be, yeah. We'll get to that though. So SAS does transfer over, and so does SSS, right? We put a little squiggle after it to show similarity. You can also write SIM or SIM dot.
Well, aren't they all because you have the...
Let me show you another one. I know these two triangles to be similar. So let me make this full triangle out, right? And I know they're similar because their parts will be proportional. Alright, so check it out. I've got this angle, this triangle. It's kind of weird looking. That's 4, 2, and 3. So I'm going to make, I don't want to make that. I want numbers. So let's do 4, 4, and 2. Alright, so it happens to be isosceles. Deal with it. Alright, and then I've got another triangle I'm going to make that's proportional. So I'm going to need the sides to be what? 2, 2, and what?
1.
1, yeah. If it's going to be proportional. So these two triangles are definitely similar, right? We know that by SSS similarity here, right? 4 relates to 2 the same way 4 relates to 2 the same way 2 relates to 1, right? There's a doubling or halving going on here, depending on how you look at it. Now, notice something. When they're similar, check out their angles.
I'm
Shocked. So
They're exactly the same, right? So triple angle is enough to prove that something is similar. It's not enough to prove for congruency, right? Because here's two angles that all match up, right? Two triangles that have all their angles matching up, but they're obviously not congruent, right? But they are similar, right? 2 to 4, 2 to 4, 1 to 2.
So it can't be similar.
So triple angle works. Now hear me out, hear me out. Let's play a game, let's play a game. I'm gonna name 2 angles in a triangle and you're gonna tell me the third angle, okay? I've got a triangle with 2 angles. One's 90 and one's 30. What's the third
60.
angle? 60! Very good. It has to be. Why? Because they all add up to 180. So if I've got a triangle with an angle of 10 and an angle of 20, what's the third angle?
160.
Try again.
150.
150! That's right. Because they all add up to 180. So hear me out. If you know 2 angles of the triangle, do you know the third? Yeah, you get the third for free. So if you found 3 angles all matching, good for you. You did a little extra work. All you really need is 2 angles, right? So angle is enough to get done.
Angle?
For similarity, yeah. If you know 2 of the angles, you get the third for free, right?
Do people ever write that though?
Isn't that angle addition
Just
possible?
angle.
To get the third angle, yes. Yep. Or internal angles of triangle theorem. But yeah, either way. So, and here it would be angle addition because I haven't talked to you about that theorem. Now, look at these guys over here. I want you to figure out the rest. Do these transfer over? And if they do, great. Tell me why.
When do we do that?
Don't be afraid of being wrong. Laney, which ones do you think transfer over and why?
Side angle angle.
Why do you think that is?
Because if 2 angles are the same, so are their parts. 'Cause
Hey, so does
Right?
ASA.
If we have 2 angles that are the same, then we automatically win. So if we have 2 angles that are the same and a side, great, you overachieved, right? So this one doesn't have its own thing, but it's kind of taken care of by this, right?
And so was the other one.
And so is the other one, right? 2 angles, right? Doesn't matter if
I
it's the
think
same.
HL does too.
So
I
is
think that's
that
after
why
the ball.
ASS doesn't work?
Could it?
HL's
Kind
the
of.
curveball, Mr. Mac.
HL,
No.
does it transfer over or no?
Yes.
Yeah.
Yeah.
Why can't ASS work?
Because if we have two sides, so we have an angle that's set in two sides, there's two different ways you can make that triangle, and so it wouldn't be congruent.
Yeah, one HL,
Trust me on that.
HL would have to work, right? Because
So ASS doesn't work for congruency, because if you have one angle and then two sides following that, there's two different ways to make that triangle, which means we don't know which one we're talking about, so we can't prove it congruent. We know it's one of the two triangles, but that's it. With HL, which is a special case of ASS, right, we know the 90 degree, and that locks it into one specific triangle.
So it's
Okay? So it takes it down from two possibilities to one. Trust me on that. Great question, though. All right, HL, why do you think it has
I
to
think
transfer?
it has to work because when you make a 90-degree angle, doesn't it automatically set the other two to make it?
Let's mess with that. All right, so check it out.
Because you're gonna have to break down.
I'm going to make a 90-degree triangle. I need a hypotenuse and a leg that are proportional, right? So I'm going to make a hypotenuse and a leg real quick, just by doing this. Okay? So I've got a hypotenuse and a leg. How do I know that's a hypotenuse? Because I've got 90 degrees here. Cool with that, right? So I've got H and an L. You can imagine another triangle over here that's similar, right? Now, here's the problem with it. Actually, I'll do the triangle for you. So if that's 4 and that's 2, to make it easy on myself, I'll make it 2 and 1. So here's 2 for the hypotenuse, and here's 1 for this. Okay, cool. So I'm going to shrink those down to be congruent. Okay, they're as small as they can be. No, I don't want a small, I want 90. Okay, so there we go. So these two, right now, I have a hypotenuse and a leg. Will they be proportional? Yeah, because it locks in the other side, like Sasha was saying. But here's the deal. I assume that these angles are matching, right? What if I do it like that? Then they're not, right?
You don't have a.
All I have is that I know that the 90 has to be there, and the two sides, hypotenuse and leg, right?
You would prove that you would have a 90.
Boom! Exactly. Check it out. As soon as I change this angle, now I don't have a 90 anymore. So the 90 doesn't just lock in the two sides, but it also kind of locks in this angle, doesn't it? Right? It has to be that angle in order to make it 90. And so what we have here is two angles that we know, right? A 90 and whatever that is. So by AA, they have to be.
So I get
I'm going to do that again. So check it out. I know that these are similar, right? Because I have two similar sides and they both have 90 degrees, right? I'm good to go. And it locks in that third side. So by triple S, they would be proportional, right? But I assumed what these angles would be, so I could change it. But the problem is that if that's not that angle, do I have a right angle here anymore?
No.
No, so we're not talking about right angle triangles anymore. In order for it to be HL, I have to have a right angle triangle. So yeah, that kind of locks in both angles. And if we lock in both angles, then by AA, they're proportional, right?
Yeah.
Can I combine all of them?
all those three?
Yeah, so if you know one of these, then that means that all the sides must be proportional as well.
Yeah.
It's kind of, so you know CCP, right? Once you have one, kind of everything opens up. Same thing with this, with CSP, corresponding similar particles.
Oh.
So yeah, they do kind of all relate, right? So, but the bare minimum you need before it opens up the whole world to you are these three. HL's covered by AA. Same thing with ASA and SAA. The other two have their own. Cool. SS is not enough, but two S's and an angle between them, yes.
Why isn't SS?
SS isn't enough because if I have two sides that are proportional, right? I have two sides that are proportional right now. It doesn't say anything about the angle, right? So ta-da! Nope, not the same. That's going to be non-proportional to that. So SS isn't enough to get the job done. Now if I have SS with an angle in between that's set, yeah, it locks it in, right? See how that makes sense? Red. Awesome. How do you feel? Are you with me on this?
Great.
Again, I can't prove these things. Otherwise I would with algebra, and you'd hate it, right? These are postulates. I can show you examples and reason with you and be like, look, man, it's got to be that way. But we can't prove this. It's a postulate. It turns out all of math, all of this proving and theorems and everything, all come down to postulates eventually. The basis of what we build everything around. At its very basis, geometry, like most things, is a leap of faith. We have postulates at the very base of it. Some things that we just have to accept to be true, because they aren't. How could they be anything else?
That's right.
Now, if you can prove a counterexample, then those postulates are bunk, and then everything that we built them upon crumbles. But so far, we haven't found a way where this can't be true. So these postulates, just like these ones, are true.
So who had to authorize all this to make sure?
Lots of mathematicians over time. It's kind of like the scientific process, right? We keep testing it and we see, yep, there's no other way to go about it, right?
So theoretically, there is a way to do it with 7 pounds.
Until we can until we can prove it wrong, we assume it to be true in this case for postulates.
So
we don't
is
like
there-
doing that.
Has there been a postulate that's been
I'm gonna do it.
disproven?
Yes, Euclid had a postulate about parallel lines that it wasn't a postulate. They said that we could he said it had to be something we just accepted, and someone later said, no, I can actually prove it, so it's a theorem. Does that make sense? Right? So they were able to use the other postulates to prove it, and so they said we don't need to have that as the foundation anymore. We could say that.
What that one?
Yeah, they built into something else, right? So when you're making a geometry, and everybody's geometry is different, we're studying Euclidean in here, right? It's really what we assume to be true, and then built from there is what that geometry is based on. So Euclidean geometry has these as postulates. Other, so it would be like, no, I have different postulates, and I can use those to prove this, right? But at the basis, these guys are things we're accepting to be true.
So if I change one postulate, does that change all of geometry?
Kind of, right? If you prove one wrong, it kind of makes the whole thing come tumbling down.
Yeah.
Not all of the house of cards will fall, but everything that's connected to
I
that.
want to do that.
That'd be cool, right?
Yeah.
There is a theory out there. It's called a hypothesis. So when we are talking about geometry, there's this thing called the Riemann hypothesis. If you can prove it, you'll get $1 million. It's one of the Millennium Problems, and we have based a lot of mathematics on that being true, and it's worked out really well. Like everything is falling in place, and it's allowed us to get men on the moon. It's done all kinds of stuff, but we don't know it to be true. We've assumed it to be true. It's a Riemann hypothesis, right? We assume it to be true because it works with everything. Now, if you were able to prove it wrong, then we'd be like, oh, crap, right? We got to readdress everything. But so far, it has always worked. And so we believe it to be true. We'd like it to be proven, right? But that's one of those things. Actually, math, there is a theorem that states, theorems are provable, right? So this is proven fact that it is impossible to prove everything in mathematics. Some things have to be a leap of faith. It's not that we just haven't figured it out yet. No, it has to be. It's called the Gödel incompleteness theorem. Math is incomplete. At some point, we have to take a leap of faith.
I don't have a
That's
proof all
the
of
point we
math
should
wrong.
Beautiful, isn't it?
Because words
No.
were just
Isn't
created
that
by
poetic?
some person. Self-reading.
All right,
Anything
no
you
let's get into the homework.
Think about it.
Everybody's got one of these, right?
Sure.
No. Yes.
Awesome. Schlaffer was in charge of passing them out, so I'm sure half of you don't have them. All right.
Yeah, they're all done.
A, B, and D are line segments, and they're parallel. That's fun.
We did this last week and I failed the test.
Nope, this is different. This is kind of similar to like 2 weeks ago. All right, so we want to prove not that the triangles are congruent, but that they're similar. That's what that little squiggle means, the tilde. Now, there are 2 triangles in this diagram. There's the one on top, and then the one that is here, right? The whole thing. 2 triangles. We're going to prove them similar. Now, the only way they'd be congruent if somehow I really was sucked at drawing diagrams and DE was actually AB, right? Otherwise, at best, we can prove them similar, right? They don't look like they'd be the same. If for some reason I drew this diagram really poorly and I drew DE up here when it should have been AB, then we'd say they're congruent. But we don't know that, so we're going to prove them similar. This triangle is similar to that triangle. What we need to do that, we've already decided, is either AAA similarity, right? 2 matching angles. We need side, angle, side, so 2 proportional sides, not matching, right? Proportional, right? Like 3 and 6 and 4 and 8. And then a matching angle in between them. Or 3 proportional sides, right? Like 3 and 6, 4 and 8, 5 and 10. Now, did it give us any information about the sides?
No.
No. There's no way you're going to get that. If you imagine, I could stretch this downward and still be parallel, right? But it would change the relationship of how big these things are, right? So we're not going to be able to find any side stuff, so just forget that. What we need is 2 angles. So what do you think we should do? Yeah.
Well, I was gonna ask, like, if it doesn't give you any numbers.
Yeah, about the
angles,
sides.
Is it even possible to solve?
It's not possible to do anything but the sides if you don't know anything about the sides.
No, it didn't give us anything about the angles or the sides.
Yep, but it's possible.
Can you drop a line down?
Can I what?
Drop a line down?
I can, but we're not going to do that. I'm not going to do that today. That's not a bad idea.
Did you just say 180 divided by 3?
We've already got our 2 triangles. We're not going to need to do that, but it could help, but not right now. What else?
What angle? CD and CBD.
These 2 angles right here?
Yeah.
What about them?
Wouldn't they be like linear pair?
Nope, linear pairs like this angle and that angle, right? Adding up to 180,
Yeah.
right?
Well,
These 3 all add up to
180.
180, but these 2 definitely don't,
Of course.
right? Because the whole triangle had to be 180. What else?
Can you do anything with, like, how the fact that, I don't know, I'm just saying it, but, like, Angle BED is obtuse. Can you do anything with that?
Well, these two would be a linear pair, but that's not really that useful.
Does it have something to do with what we just did with the numbers and then put the numbers in the center?
Nope, we don't need that.
Well,
You should give us a hint.
It's a good guess. Go ahead, Alicia.
You take 180 divided by 3. It's good for me.
Say it again.
Like for the big, like the whole big triangle, right?
Yeah.
Take 180 divided by 3 grand.
You could if you knew all three angles were equal, but we don't know that.
They both have angles.
They could be different. That could be 30, that could be 60, and that could be 90 for all we know, right?
well,
Yeah.
Good thought.
Can you?
That cap angle CDE is congruent to angle A.
Okay, check it out. When we have parallels, it's okay. When we have parallels, right, what should we be looking for?
Transversal.
Transversal corresponding angles, exactly, right? So let's extend our parallels if you don't see it. That's a good way to see it. So always extend your parallels, that can help you see. Let's do L for Laney, K for Kozovic, M for May, and R for Rosie. So we're going to say let LDEK, Ledeck, and let MABR.
that should be your team name.
Mabber.
Yeah.
Okay,
I think you mean double.
I'm not going to extend this, but see how that's a transversal, cutting two parallels, right? What do you see?
Wait, where did you put LM?
I'm interested in angles inside my triangles.
CDE
This angle right here, CDE,
is, and then CAB.
CAB is the same.
Yeah.
By corresponding angles postulate. They're both the top right corner of their intersections. Do you see that? So by CAP, angle, I have to call it CDE because I have lots of angle Ds, right? CDE is congruent. Again, it's congruent. It's still cap, right? We're not doing similar here. They're congruent to CAB. You could also call it angle A. But actually, no, you can't. We have two angle A's now, right? CAB.
I can use it
Yeah. All right. Now we've got matching angles, so we have one of the A's. We need to get another one. Now, we can do the same thing on the right side, right? Corresponding angles here and here. And you'd be right. These two angles would be congruent. Would we know that they're congruent here and here? No. Not necessarily, right? But there's another way we can get another angle. Let's not use these. What do you see? Lainey?
The angle CEK corresponds to EBR.
Yes, so these two angles would be the same,
But
right?
vertical angles.
And then here we get those angles, that's true. But that angle tells me about like this thing, and I'm not interested in that.
What?
That's a good thought,
They
though.
would have angle C in common because they both.
Boom. Do you see how both share that angle? So what you guys said was good, and you're going to give me a lot of information that's great, but not what I want. It's kind of like that game we played earlier, right?
No, we have
You're
fun.
right. So like what Lainey said, she's absolutely right, but I'm trying to streamline it so you see what I want you to see for now, okay? So he's right. Check it out. This angle is shared by both triangles. Do you see how the big triangle uses angle C, and the little triangle uses it? So before we had vertical angles, and you guys were like, "Oh, they share an angle." No, they don't. We have an angle up top and an angle on the bottom. They're separate angles, right? They happen to be the same value, right? But they're not the same angle. There's one up here and one down here. This is the same angle for both triangles, right?
So
we call it bi-shared angle. It's kind of like a shared side, right? Bi-shared angle. Angle C is congruent to angle C. So yeah, you could go over here and get these other guys by cap, right? But you could also just do this. And now you've got angle, angle. So we say bi angle, angle, the triangles are similar. Angle, angle, similarity, remember? Not angle, angle, congruency, so you have to put the little symbol after it. Triangle ABC, that's the big one, right? Is similar. Do not write congruent. They are not. We don't know that. They could be, right? Because similar triangles can be congruent.
What does after the A, what's the squiggly mark?
That means similar.
Is
A similarity, right? Triangle ABC is similar to triangle. Let's match them up. A goes with D, right? B goes with E. And C goes with itself.
Do we also have side angle side?
We don't have any sides. We don't know anything about it. It looks like it's in the middle, but we don't know that.
I have a
Wait,
feeling.
how'd you find it again?
I did cap, right? And then I had shared angle here. Because the big triangle uses angle C, and so does the small triangle. They have shared angle.
I'm going on the limb, but as soon as you
Okay?
see the
We could have also done cap twice, right?
Sydney.
And got it done as well.
Yeah.
How do you feel about similar triangles?
Lane.
Now, why is this useful? If I knew this was 3 and this whole thing was 6, and I knew this was 4, 3 to 6, 4 to 8. Right? Now, they didn't give us that, right? I'm just saying, for instance, that could help us solve a problem like that. Let's look at number 2. What do you see?
I see.
It says BD is a line segment. That's all that means. It means that BD is a line. There's
I
no
see
bend at
vertical
C.
angles.
Scissors.
Yes, so there's no bend at C, so we have an X here. Same thing with AE. So that's vertical angles. They also gave us B and E were congruent, right? From here.
Is it relevant?
So by vertical angles theorem, these two angles are congruent. Can't call them angle C because we have multiple angle C. So I'm going to call it BCA congruent to angle ECD.
What?
Are the triangles similar?
No.
Yes.
Yeah, angle.
Yes, by angle, angle. We have two angles, so we're good. By angle, angle similarity, triangle ABC is similar to the other one. Now, let's match them up. All right, A goes with what? Well, check it out. The measure of this angle down here for angle A, isn't that going to be equal to 180 minus purple minus orange,
Yep.
right? Well, this angle is also 180 minus purple minus orange. So they're the same, right? That's kind of like if you get two angles, you get the third for free. So A and D do go together. Again, I didn't need that for my proof,
I see what you're looking.
right? But I know they have to go together.
Look at the top one.
B and E go together, and C go together. Yeah, that's true. It should be, right? But I'm going to give you proofs eventually that aren't always provable.
Not true.
Also, I make mistakes sometimes.
Whoa. Do you have kids?
No, haven't made that mistake
Wouldn't
yet.
you know that?
All right, as far as I'm
Yet.
aware. Right before you tap.
Yeah,
These
go
triangles
for
are
it,
similar.
Idiot.
How do you feel about that?
Well, you're not
Are they congruent? Maybe.
Put that out of the garbage.
But we do know that they're related,
Oh, that's
right?
yours. I thought that was mine.
No.
Next one. Mother of God.
I thought you put that out of the garbage.
Don't care. Angle C and angle DEA are the same measure. That's what that little M means. Oh no. That's what that little M means. Measure of angle C, which is this guy, and measure of angle DEA are the same. And what's their measure? 90. So we have two 90-degree angles here. We're going to prove that AD, this segment by here, that however long that is, if we multiply it by BC, that'll get us the same number as if we multiply AB by DE. What? We don't even know what the sides are. How do we know that? Here's how we know it. Let's prove the triangle similar first. What do you see? Not yet. We only have one pair of angles. We need another pair. Right? Does that make sense? AA stands for two pairs of angles. Like two pairs of shapes.
No. That's no.
We don't have any vertical angles. There's no X's.
Nope.
What do you see?
Linear.
I see.
Yeah, we have a linear pair, but that's going to get us an angle about this guy, and I don't care about that guy.
I
right?
see HL.
HL? Hypotenuse leg? We don't have any matching hypotenuses for legs yet.
How do you know?
Well, we don't have any marks for any of the sides. They'd be matching to the HL. Do we have a hypotenuse? Yeah.
They share.
But we don't know.
They share A.
Boom! They share angle
Rosie,
A.
get out of here.
Haley, get out of here.
So by shared angle,
If I make this, we use no card on the text.
angle A is congruent to angle A. That's by shared angle. Do we have enough to prove the triangle's similar?
No.
Yes. Big
Okay.
triangle has an angle and an angle. Small triangle has the same angle and angle. So by AA, they're similar. Angle, angle, similarity. Triangle ABC, that's a big one. Similar to small one. A goes with A. None of you are seniors. B on the big triangle is this angle. What angle must that go with on the small triangle?
285.
D, right? And C goes with E. Now, if the triangles are similar, which they is, we'll get it next time.
See you tomorrow.
See ya.
I'm the only boy in the big train playing Sharkers in Tower. What?
I swear to God, if I'm not here.
Yeah.
I'm
It's
gonna
be
kill
okay.
him.
Nope, but I
Yeah,
know.
she is.
Right, tell her if she wants to talk, I'll find me on Instagram or something, okay?
Are we doing dozens?
Yeah, we are.
Hey, nice.
Troy!
Yeah, baby. In the breeze, in the wind. You ever seen Snoop Dogg? White guy that helps. No.
Mr. Mac, what are you guys doing with these cups?
Name's Todd, baby.
You know.
Where are you?
Oh my god. I hate
Snoop Dogg.
school.
Alright.
This is a good class for class.
Thanks.
Is that supposed to be geometry?
Yeah, it's basic geometry.
Oh, basic geometry?
Oh, selfies, selfies.
Oh, it's regular geometry. Here you
No.
are. It's not easy.
No.
Oh yeah, you gotta do that.
Okay, but I teach it.
Will you make it easy?
Yeah. Ish. It's a real class.
It's a real
I
class.
actually make it harder because most geometry teachers don't really know how to teach geometry.
Like one you have to have five.
Easier and regular.
No,
Most
my
teachers
God.
You don't only jump.
I'm really that smart? What is my guess?
Right.
We're writing on it.
I just skipped that.
Where's Olivia?
I don't know.
I'm gonna need you to sign my paper.
Okay, cool.
Alright.
Make sure
I
you have
can?
your Chromebook
Sweet.
for Desmos. We're going to talk a little bit before we get into it, though, so make sure you're sitting in a seat where you can learn.
There you go, Mac.
Rad. But that's the idea.
I'm gonna leave now.
So, geometry,
What are you doing?
the way I teach it is not a blow-off class. When I took geometry in high school, what most people do, it's the class that all math teachers hate to teach because they never actually learned it, because no one actually knows how to really teach it. It's just like memorize definitions and memorization in the class, right? Worse than algebra. The way I teach it, because I actually learned how to do it and how to figure it out and really how to do geometry, I make it work really hard.
Oh,
My stuff will kick your butt, but you will come out smarter than you've ever been.
What if I?
My geometry kids could run circles around other geometry classes in this country. Circles, and I don't mean that as a joke. Hi. Yes, go, hurry.
Okay.
That's fine.
I'm gonna go with
Coming
her.
to finish my last question.
Awesome.
Getting 100.
When I taught geometry last year, I taught it with another teacher. Here I'm the only teacher, right? And that other